Okay, we're going to continue on here. Chapter 8, what we were talking about. Who knows? I don't know. Chapter 8. I think we were talking about here a couple things. We talked about atomic mass, I believe. And the atomic mass, again, is what we see on the bottom there of the periodic table. And remember that when you pull off a number there, you can use it as, for example, for hydrogen, 1.00 AMU per atom. And again, an AMU is an atomic mass unit. We also talked about how to calculate the atomic mass, and we can calculate the atomic mass by taking the percentage of the first isotope times the atomic mass of that first isotope. We then add it to the percent abundance of the second isotope. Again, how often it occurs sort of naturally, and times it by the atomic mass of the second isotope. And then we just kind of continue this pattern for all the naturally occurring isotopes. A reminder that, again, the number that we see on the bottom there is a average value of all those naturally occurring isotopes for that particular element. We got into really a couple other important things, which was our friend Avogadro and his number. And Avogadro's number there is 6.022 times 10 to the 23. Remember that the units of Avogadro's number can change depending on the situation. The two popular units that we come across usually are atoms, or you can do molecules, or really any unit that you want to use with it. And remember, that is what technically equals 1 mole. And again, the abbreviation MOL is a mole. And the importance of Avogadro's number is we use it whenever we have anything that involves atoms or molecules or particles. Either they give us a number that has those units, or we're looking to solve for something in those units. And it's really our conversion factor to go from moles to atoms, or again, molecules, if that is the case, and backwards. So it's really Avogadro's number to do that. The sort of conversion factor that we use really more often than not is molar mass. And molar mass has units of grams per mole. And molar mass is also taken really from the periodic table. And that is typically how we use that number on the bottom in this more sort of useful unit for us, since it involves grams, which you can sort of easily weigh out, say on a balance or something like that. And it is numerically equal to the atomic mass in AMU per atom. And we do go 4 significant figures on it. So if we had something like hydrogen, we would say that there's 1.008 grams per mole. Again, we can use that as a conversion factor. The number always stays with the grams part, and it's always per 1 mole. We also, if we had a molecule or something like this, we just add up the parts like we talked about. So in this case, there's again 2 hydrogens and 1 oxygen in this case for 16. And again, these numbers come from the periodic table, and that'll give us something like 18.02 grams per mole would be the molar mass of water. Now, molar mass is a really important sort of conversion, and it is used to do things that we do a lot of calculations, which is go from grams to moles and moles back to grams. So again, these guys are used a lot to do that conversion. And it really is the moles that sort of tie both of those things together. If you have to go from sort of one extreme to the next, it is the moles that are in between that. So say you had grams and you want to get to atoms or molecules, the sort of stopover there in the middle is usually moles. And again, going in this direction or that direction, that's going to be your molar mass. Going this way or this way, that would be your Avogadro's number to do so. So that's sort of the thing that ties them both together, is that moles in the middle there. So just like for hydrogen, if I had 1.008 grams of hydrogen would equal 1 mole of hydrogen, and 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. So again, as you can see, the mole sort of the guy in the middle. And the same thing if we had like our waters we talked about, water would have 18.02 grams for every mole of water. and a mole of water would also have 6.022 times 10 to 23 molecules of water. So again, that sort of mole is the thing that ties them together. The other also important thing that we talked about last time, again, is whenever you need to calculate molar mass for something, you should do it based on just the formula by itself. So if it happens to be in an equation, as we talked about, has a coefficient or something like that, always just take the formula for whatever you're trying to calculate the molar mass from, and just one formula by itself. And that's really what the grams per 1 mole represents, is basically you just have one of those sort of formulas and stuff like that. Any questions on any of that stuff we talked about last time? So we did some examples, and before we kind of continue on to the next part of this chapter, I did want to talk about another sort of calculation that sometimes we may need to do. So for example, let's just say we had 45 grams of C2H6O, and we wanted to know how many hydrogen atoms that would be. So in this particular case, we are ultimately not interested in the entire thing there. We're not interested in the ethanol there, the C2H6O. We're actually only interested in the hydrogen part of it. And we need a way to go from like the whole thing to just the hydrogen part. And we could actually use the formula itself as a conversion factor to do so. So for example, when I look at this formula of C2H6O, I could say for 1 mole of the entire thing, we could look at these coefficients that are there, and these will represent also the moles of each of those elements. So for example, if I was interested in just carbon, based on the formula, and 1 mole of the entire thing would give me 2 moles of just carbon. And again, that's basically the bottom number that we see there in the formula. That would mean in 1 mole, this entire thing, how many moles of hydrogen would I have? It would be 6 moles of just hydrogen. And if we were maybe interested in oxygen, we could do the same thing here. And that would be 1 mole of oxygen. So in some cases, you may be given a calculation where you're not maybe interested in the whole thing, but maybe one of the elements that are present in that particular compound. You could actually use the conversion, the formula as a conversion factor, sort of a mole to mole conversion. That also means that in order to use that conversion, I would need to get my original number here into moles, so everything cancels out. So the first thing that I want to do is convert my grams to moles. And obviously that's going to be our molar mass, as we talked about. And in this case, we want to convert it for the entire thing. I think we calculated in the previous problems, this particular guy. And we'll recalculate it again by just going to the periodic table, adding up all the parts there of it. So again, that's basically my carbon, my hydrogens, and this is my oxygens, basically. And if I do all that, I think it was like 4607, if I'm not mistaken. Let's try that there. 4607. Mega memory course is paying off. 4607 grams per mole. So this would be the molar mass of our entire thing. And again, we really need that to use as a conversion factor to convert from grams to moles. So the first thing that we would do is we would take our 45 grams of the whole thing here. We would use that as our conversion factor. So opposites cancel, which means I want 4607 grams per mole of the whole thing up on top. If I stop my calculation right here, I would be in moles of the entire thing. So that's going to now allow me to use my conversion factor here that I got from the formula to go from the whole thing to just the hydrogen in this case. So by setting up with our dimensional analysis, we can see the whole thing's on top. So to get rid of the whole thing, it goes opposite, right? So we're going to go 1 mole of the entire thing gives me 6 moles of hydrogen, right? Moles of the entire thing are going to cancel. And now I would actually have moles of hydrogen, which if I wanted to know how many moles of hydrogen there was, I would be done, right? If I wanted to know how many grams of hydrogen, I would need to use what to know, go from moles to grams. I would need the molar mass of hydrogen alone, right? But in this case, I'm not interested in moles. I'm not interested in grams. I'm actually interested in atoms, right? And that is the key word that tells me what I need to use for that. Avogadro's number, right? So that's the key that I need to use Avogadro's number here. So we would use Avogadro's number here to finish it out. A mole would go on the bottom. Avogadro's number in this case would go up on top because that's going to leave me atoms when I'm all done. The moles will cancel. And in this particular case here, 45 times 6 times 6.022 to the 23 divided by 4607 gives me something like 3.53 times 10 to the 24 atoms of hydrogen are present in this particular compound. Questions on that there? So sometimes you can use the formula as itself as a conversion factor if you're not interested in everybody that's there, but maybe just one of the elements. Again, the little subscripts on the bottom can be thought of as the moles of each of those things. So again, you can kind of use a mole to mole relationship. Any questions on that there? All right, so let's then talk about the rest of the chapter here, which is the molecular formula. So a molecule, as we talked about, is the arrangement of the elements and the atoms that are present. A chemical formula tells us the symbols, and a molecular formula basically will tell us exactly what elements are present. And the molecular formula will tell us exactly what's there. And sometimes it will give us some other information. And sometimes it will just be a basically, these are the things there. And it won't give you any other type of information like structural information. So sometimes people write molecular formulas to give you some information about how things are sort of connected and bonded together. And in some cases, molecular formulas are just simply what's there in terms of their elements. So when we look at the molecular formula, it tells us exactly what is present. And again, simplest sort of molecular formulas are going to be our diatomic molecules like hydrogen, nitrogen, oxygen, and fluorine. As I mentioned before, and we've been looking at ethanol, which is the C2H6O, which is a molecular formula. Sometimes people may write it as CH3, CH2OH. That is also the same thing. But this guy here gives us more information about how it's actually connected. If we were to draw ethanol, it would look something like this. So you can see the second formula, CH3, CH3, CH2, CH2, OH. OH gives us a lot more information about how it is sort of structurally put together. But if you count up all the parts there, you still have 2 carbons, you still have 6 hydrogens, and you still have 1 oxygen, while this formula here doesn't really give us all that information. Another very common one is like acetic acid, which can be written like this, CH3, COOH, or a lot of times people will write acetic acid, C2H4O2. They are both molecular formulas for the same thing, even though they may not look like the same thing, but they both have the same amount of everybody. This guy, again, just gives you a little bit better understanding of how it's put together. If you were to draw acetic acid, which is the major component of vinegar, will look something like this. So CH3, CH3, and this is basically this group right here. And again, it gives you a little bit more structural information. So again, sometimes molecular formulas will give you that structural information. Sometimes they won't. And sometimes people get confused, like they see it written two different ways and they think they're different things, but they're really not. Any questions on that there? Now, an empirical formula, on the other hand, an empirical formula is the simplest whole number ratio of what is present. So it does not necessarily tell you sometimes exactly how many of each atoms are present of each element, but it will give you the simplest ratio of those atoms that are present. So if we look at hydrogen peroxide is basically 2 hydrogens for every 2 oxygens. That is the same thing if you divide by 2, 1 hydrogen for every 1 oxygen. And that is how we would get our empirical formula here of HO versus our molecular formula here of H2O2. Now, sometimes both the empirical formula and the molecular formula are going to be the same. There's no way to reduce it down anymore and still get whole numbers. By the way, all these numbers on the bottom do need to be whole numbers. Can't like have a half atom or anything like that hanging out or anything like that. So for example, we look at water. Water is 2 hydrogens for every 1 oxygen. There is no way to reduce that down any further. So water is both the molecular formula and the empirical formula. So sometimes they are the same, and it's a situation where you are already at the simplest ratio. One things that always are the simplest ratio are ionic compounds, right? When we put an ionic compound together with our positive ion and our negative ion, we do it in the simplest way to get to 0. So when you write a proper ionic compound formula, they are always the empirical formula because they always should be the simplest way to get to 0. And all ionic compounds are basically formulas are empirical formulas because of that. So if we look at something like hydrogen here, N2H2, that is 2 nitrogens for every 4 hydrogens. And again, you can divide by 2 and still get whole numbers, which means you have 1 nitrogen for every 2 hydrogens. And that will give us our empirical formula in this particular case. As I mentioned before, it is only really the molecular formula that always tells us the true atoms that are present. And again, the empirical formula is usually that simplest whole number ratio. The empirical formula is usually the one that you would find in the lab. It's very easy to do by just taking differences of masses. You can very easily sort of calculate the empirical formula by doing so. And here's a few other examples of ones where both the molecular formula and the empirical formula would be the same. Carbon dioxide is 1 carbon to 2 oxygens. There's no way to reduce that down to still have whole numbers. And the same thing, obviously, with our NH3. There's no way to reduce that down any further as well. All right, so take a moment here and write the empirical formula for each of. Okay, let's take a look. So in this case, for the first one, we basically have 2 carbons for every 2 hydrogens. We clearly can divide everybody by 2, which would give us an empirical formula in this case of 1 carbon and 1 hydrogen. For the second one, we have 2 iodides for every 5 oxygen. That's pretty much as low as you could go. You cannot reduce those down and still have whole numbers. Once again, you cannot have a half of, atom or something like that. So that means that this would also be the empirical formula. And lastly, here we basically have 6 carbons for 12 hydrogens for every 6 oxygens, which means we can go through and divide everybody by 6, which would give us basically 1 carbon 2 hydrogens and 1 oxygen, which would be our empirical formula. Any questions on any of those there? So if you have a molecular formula and you really just want the empirical formula, you want to look and see if you can reduce down everybody by a common number and again, still get whole numbers. That's the important part. You can't get any decimals or anything like that. Any questions on that there? So let's talk then about percent composition by mass, which is very commonly used when dealing with empirical formulas. Percent composition by mass pretty much is what it sounds like. You take the percentage of the element you're interested in to find. So you would take the grams of that particular element in that compound divided by the grams of the total compound and times it by 100%. So you basically would get the molar mass of the entire compound. You would get the molar mass of each of the individual elements and divide it out and get the percentage of each of them that are present. So let's take a look at one here. Let's say we had hydrogen peroxide. So really the first thing that we would want to do in this particular case is get the molar mass of our hydrogen peroxide. So that's going to be 2 hydrogens at 1.008 from the periodic table. That's going to be 2 oxygens at 16 from the periodic table. So this is really going to give us our mass of our entire compound here. So that's like a 32 and a 2, basically. Can give us 3402 as the molar mass here of our H2O2. So in this case, if we want the percentage of hydrogen, there are 2 hydrogens, each at 1.008 in this formula. We would divide it by the molar mass of the entire compound. And then we would times it by 100%, which means in this case, we would end up with a percentage of approximately, we'll go with 5.926% hydrogen. If we wanted to do this for oxygen, we would do the same thing. We would take the percent oxygen, and in this case, there's 2 oxygens, each has 16. So that's the grams of our element divided by the entire molar mass of our element compound times it by 100%. So that's going to give us 32 divided by 3402 times 100, going to give us 94.06% oxygen in this case. Now, we can see by mass, right, this particular compound is made up mostly of oxygen, right? What else I could have done, right, is in this particular case, since I do have the hydrogen and oxygen is the only other element present, I could subtract 100 minus that number, right? And I could have took 100% minus my 5.926 and got there as well. And that is because, right, that makes up 100% of the compound, the hydrogen and oxygen. So if you just have one left, you could basically just subtract 100 from it, and that would give you your other number. Or you could just do the calculation. Any questions on that there? So let's take a look at HO, which is our empirical formula. Why don't you calculate the percent composition of each of those there based on HO's formula? Do the same thing. We'll start with our molar mass. In this case, we only have 1 hydrogen in our empirical formula and 1 oxygen. Makes it not too bad. That's going to give us a 1701 grams per mole is the molar mass here of our HO. The percentage of hydrogen in this case would be 1.008 grams per mole divided by the molar mass of the entire compound times 100%. And that is going to get us there 5.926% hydrogen. We'll do the same thing here for our oxygen, which also has just 1. And in that case, it's going to get us here 9406, basically. Are the numbers the same or different? They are essentially the same, yeah. And they are the same because they are related to each other, right? One is just a simple ratio of the other, which means they're going to have the same mass ratio as well. So the percent composition of the elements in the empirical formula and the molecular formula will be the same because they're basically the same ratio of each of those elements being present. Any questions on that there? All right, let's try one more here. A little phosphoric acid, percent composition of each of these guys. Hydrogen is 1.008. Phosphorus is 3097, I think. Yeah, we'll go with that. And oxygen is 16, right? All right, so we'll start the same way. We're gonna get the molar mass here of our phosphoric acid. So that's gonna be 3 times our hydrogen from the periodic table, plus 1 of our phosphorus there from the periodic table, and 4 of our oxygen from the periodic table. Adding all that up, that's like a 99 grams per mole. So we can start with the hydrogen, our percent of hydrogen, since there are 3 of them, we'll get the mass of just the 3 hydrogens up on top, divided by the molar mass of the entire compound here, times 100%. And that's going to get us 3 times 1.008 divided by 97.99 times it by 100, about 3.086% hydrogen. You can do the same thing here for our phosphorus. Since there's just 1 phosphorus, it'll be 3097 up on top, divided by the molar mass of the entire compound here, times 100%. And that will get us 30.97 divided by 97.99 times 100, about 3161% phosphorus. At this point, you do have 2 options. You could add those 2 numbers together, right? And then since oxygen is the only one left, you could take 100 minus the number that you get, or you could just do the calculation for oxygen by itself, which would be 4 times 16 divided by 97.99 times 100%. And that's going to give you about 65.31 here percent oxygen. In this case, the major component here is oxygen by mass, right? Followed by phosphorus, and hydrogen is the least out of all the masses there. By the way, all those percentages should add up to 100% or pretty close to 100%. Might be a little higher, might be a little bit lower with rounding, but should be in that 100% ballpark. Any questions on how to calculate percent composition here? So what we're going to now talk about is how you will calculate empirical formulas if you're sort of given information. So let's talk about the steps you should follow to calculate an empirical formula. So a lot of times you may be given the percent compositions by mass, like we were just calculating, of the elements. So in that case, whenever you're given a percentage, it's good to assume that you have like 100 grams of the sample. The reason we choose 100 is that would keep the percentages and the grams the same number, right? So if you have 50% of 100, that's 50 grams, right, out of 100 grams. So keep the numbers the same. The next thing you want to do is convert your grams to moles for each of the elements. And that obviously, as we've been talking about, is our molar mass from the periodic table is what we want to do. At this point, you will have the moles of everything. So you got like step 1, step 2, step 3. And at this point, you will have the moles of everybody, and you want to divide by the smallest number of moles. So for example here, let's just say we did step 1 and step 2, and we ended up with 2 moles of A and 4 moles of B at this point. What we would do to figure out our empirical formula is, it is as simple as 2 is smaller than 4. We would divide everybody here by 2. And when we do that, we would get 1 for A and we would get 2 for B. And if we do that and we actually get whole numbers at that point, that would be your empirical formula in this particular case. And you would be done in terms of calculating empirical formula. So basically, you want to get to grams, however you get to grams. You want to convert grams to moles. You want to always divide by the smallest number of moles. And if you hit whole numbers, you're good to go. But now let's say, for example, you do not hit whole numbers. Let's say we had 2 moles of A and 5 moles of B. In this case here, we would still divide by 2. And in this case, though, when we do divide, B by 2. We do get 1 here. We get 2.5. And that would technically mean that our empirical formula would be AB 2.5. And that is not good because you can't have like a half a mole of something, right? So that is also considered too far to round. So we do not typically round too much when we're calculating empirical formulas unless it's really, really close to a whole number. Like you got like 3.01 or 1.99, 1.98, something like that. Really, really close to a whole number. So in this case, what we need to do is figure out a number that we can multiply the empirical formula by to end up with whole numbers. So for example, if I took 2.5 times 1, that is 2.5. If I took 2.5 times 2, that is 5. That means what we would want to do is take that 2 and multiply this empirical formula by it, not just the 2.5, but the entire formula. And that would give us an A2B5 as the proper empirical formula in this case. So sometimes you will not hit a whole number and it's too far to round. Typically, if you end up with something like a 0.33, a 0.5, 0.25, 0.75, those are again kind of too far to round. These are probably the typical decimals you'll see most of the time, a 0.33 or a 0.5. Again, it's got to be like super, super close to that whole number for you to be able to round. Any questions on that there? So let's take a look at one here. Let's say we had vitamin C, which is 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen. The first thing that we would want to do is just take a quick look at the percentages and make sure that, again, it does add up to 100. If it doesn't, you're missing something, and probably there should be some way to figure it out, but you would be missing. In this case, we are pretty close to 100, so we're good. So we're going to assume 100 grams here, and what that's going to do is basically just turn those percentages into grams. So that would mean that we would have 40.92 grams of carbon, we would have 4.58 grams of hydrogen, and we would have 54.5 grams of oxygen. So that is basically our second step, just get them to grams. The next thing you want to do is convert our grams to moles. So we'll use the molar mass from the periodic table for each of these. So carbon is 12.01 grams per mole. Hydrogen is 1.008 grams per mole. And oxygen is 16 grams per mole. So this is going to give us the moles of each of these guys, and we'll do that. And we'll get 4092 divided by 12.01, going to give us 3.4072 moles of carbon. 4.58 divided by 1.008 gives us 4.5437 moles of hydrogen. And 54.5 divided by 16 gives us 3.4065. We'll go with that, moles of oxygen. In this case, it's fairly close, but it does look like this guy on the bottom here is the smallest, barely. So we're going to, again here, divide everybody by the smallest number of moles, which in this case is 3.40625. 3.40625. 3.40625. That's essentially going to give us 1 there. That's going to give us a 1 there. And when we do our middle guy there, we will end up with 1.33 in this case. Any questions so far? At this point, our empirical formula would look like CH 1.33 and O. Can I leave it with 1.33? I cannot. That again is too far to round. It's not a whole number. So we just simply want to roll through 1.33 times 1 is 1.33. 1.33 times 2 is 2.66. 1.33 times 3 is 3.99, which is pretty close to 4. So that factor of 3 is going to be close enough for us to use. Once again, we want to multiply everybody by that factor of 3. So that would then give us, when we times this whole thing by 3, basically, C3H4O3, and that would be our empirical formula in this case, all whole numbers. Any questions on those steps? So again, here after dividing by the smallest, we didn't hit all whole numbers, so we had to take that additional step to figure out really a factor to multiply everybody by to get everybody into the whole numbers. Any questions on that there? So why don't you try one here? Let's see what we got going on. What's the empirical formula for 0.54 grams of sulfur, 0.538 grams of oxygen? Sulfur is 3207, oxygen is 16. Take a few moments and calculate that empirical formula. Okay, so let's take a look since we're getting to the end. We have a third number up here, which is 1.078. That is there because if you take both of these and you add them together, you get 1.078 grams. The purpose of that number is to make sure that we're not missing something, right? So if you were to add sulfur's grams and oxygen's grams together and you did not get this number, again, you might be missing another element or something like that that you would have to sort of figure out. But in this case, when we do add up those 2 grams, it does equal the grams of the sample, which means we know that that's 100% of the sample in this case. So we could go actually right into the converting into moles since they're already in grams in this case. So our sulfur, we would divide by 3207 grams per mole. And our oxygen, we would divide by our 16 grams per mole. And if we do that for each of those guys there, we're going to get 0.54 divided by 3207. 0.016838 moles of sulfur. 0.538 divided by 16. 0.033625. And by the way, I'm not rounding very much here because I'm just going to use them to divide with anyways. So I don't have to worry too much. And you probably don't want to round really strictly here. You might want to take a couple extra digits as well. In this particular case, again, we always divide by the smallest, which looks like it is the sulfur in this case. So that is what we want to divide everybody by. That's going to give us a 1 for the sulfur, and I believe a 2 there for, basically gives us 1.9969. That is definitely close enough to round to 2 in this case, yeah. So that would give us an SO2 as our